Hello, my name is Maxine Ackhurst. I'm a geologist at the British Geological Survey and Carbon Capture and Storage. And my role is to look at those rocks that are suitable to store CO2 in the subsurface and also to trap it permanently. I'm here at the Geological Laboratory at the British Geological Survey, and behind me are the boxes of rock samples that will help us to understand about these rocks. I'd like to show you how we collect the samples, have a look at some of the samples themselves, and then give you a demonstration of how fluids can be trapped, such as CO2, in the subsurface in a storage rock, and also can be trapped beneath a cap rock to be securely contained in the subsurface. I have two samples here today. One of them is a porous rock in which we would store the CO2, and one which is a non-porous, impermeable rock beneath which the CO2 would be permanently trapped. This rock, in which we would hold the CO2, is a sandstone. It's made of many small little particles that are cemented together to form a hard rock. This rock specimen is roughly 30% open space. So a third of this rock is the tiny pores that are between the particles that make up the rock. So where does the CO2 go? It goes into the spaces between the particles. I'd like to demonstrate it to you today by using this small beaker of water. I have about 40 mils of water in this beaker. I'm unable to show you how to store CO2 with the gas itself, because at laboratory temperatures and pressures, it is a gas and it would evaporate. At the depths in which CO2 is stored, more than 800 metres, roughly half a mile, beneath the subsurface, at those temperatures and pressures, the CO2 is a liquid, although it is lighter than water. So to show you how we store CO2 in a rock, and these are the types of rocks that we know from oil and gas exploration, I pour water onto the surface of the rock. As you can see, the water disappears. I can keep adding water. And still, the water doesn't collect on the top. It doesn't pour down the sides. It flows into the open pore spaces in which hold the water, which is our example for CO2 storage in the subsurface. I keep adding water, and still no water comes out of the bottom of the sample. I have poured more than 40 mils of water into this rock sample, and none has come out of the bottom. This is the way that we would store CO2 in rocks in the subsurface. So we store it in a rock, we also contain it in the subsurface, trap it permanently within a different type of rock. And this type of rock is impermeable. It does not allow water or other liquids to flow through. If we take a very much smaller beak of water, only 10 mils of water, and we pour it onto the surface of the rock, we can see that it forms a puddle on the top. As we continue to pour water, the water runs off the top of the sample, and it starts to run down the sides. As you can see, it's starting to drip. And if I continue with only 10 mils of water, none of the water has entered the rock. It has formed a puddle on the top, and it is spilled down the sides and is dripping onto the laboratory table. It is rocks like this that contain the CO2 in the subsurface. How do we know that? How can we be sure? It is rocks like these, and we know these rocks from oil and gas exploration. Rocks like these, the porous sandstone, contain oil and gas. And they have been trapped in the subsurface under rocks like these for geological timescales, for millions of years. And we will use that same understanding, that same knowledge and expertise from which to inject CO2 into the subsurface, into rocks like these, and the CO2 is contained in the subsurface, trapped beneath rocks of this caprock nature. Scotland and the UK are very fortunate. We have natural geological resources that include oil and gas, and our knowledge of the oil and gas production, of the strata that contain that oil and gas, enables us to appraise our CO2 storage resource. The resource itself is very significant. Many other countries do not benefit from such that natural geological CO2 storage capacity. The UK and Scotland's geological CO2 storage resource is in the strata that underlie the seabed. These geological formations are known from the activities, the data and the knowledge from oil and gas production. So how do we know these rocks? We know them from seismic surveys and from geological samples collected by the oil and gas companies. When you are drilling a shelf at home, you use a drill with a pointed bit. As you drill, wood shavings or dust or rock or brick fragments are thrown out around you. We also do this when we're drilling for rocks offshore. We also have a pointed drill bit, and this cuts its way down through the rock, through the layers, and all the fragments are come out, they are collected and they are analysed by the geologist. If there are some rocks that are very important for oil and gas, and perhaps for CO2 storage, we then take special samples. And we use that using a drill bit, not that one is that pointed at the end, but also that's one a bit like a donut. So it's circular at the end. It's a bit like a cookie cutter that you might use to make biscuits or scones if you are baking at home. And here are some here. At the end of the drill bit, it's got industrial diamonds that are very hard. It's attached to the rotating drill, which drills its way down through the rocks. And it collects a cylindrical sample of rock in the middle. Here we have some small drill bits. If we want a bigger sample, we would use a bigger drill bit. Again, this has got industrial diamonds at the sharp end, and as you can see, it collects a cylinder of rock. We call this a rock core sample. Here we have a bigger drill bit. It's far too heavy for me to lift up, but as you can see, this is the size of sample that you can collect. The rock samples that are collected in this way are cut into lengths by the drillers. The drillers cut it lengthways and put it in a box and lay them out for the interpretation and analysis by the geologists. Here is an example of some core samples collected from beneath the seabed offshore Scotland. The core that we have collected by using the cylindrical drill bit has been cut into 1 metre sections, cut in half lengthways and placed in these boxes. The top of this box is then be continuous with the bottom of this one, top to bottom accordingly. So this is the bottom of the core and this is the top. When you look at the core boxes, you can see 2 different colours. In this box here by my hand, the core is of pale grey sandstone. As we move up, the pale grey sandstone is increasingly brown in colour. This is because the rock is stained with oil and gas. Oil has entered the tiny spaces between the particles that make up the sandstone. The darker the colour, the more heavy the stain of oil. As we move up, this is our oil reservoir. As we move up, we can see the sandstone becomes paler brown and eventually sort of a honey coloured. There is less oil stain as we move towards the top. and eventually the rock resumes its sort of pale grey colour. We've then reached the top of the core, and at the top of the core the rocks are grey. These rocks are mudstones. These rocks are impermeable and do not allow fluids to flow through them. So these impermeable rocks are cap rocks. These trap the oil and gas that are in the storage strata beneath them. We can see from the box that we have our cap rock in grey, our mudstone, our brown oil-stained sandstone, and again towards the bottom of the core we can see another occurrence of another layer of rock, another layer of grey cap rock. This shows us that different layers of geological strata in the subsurface can contain oil and gas and can be used for CO2 storage, and are separated by different layers of cap rock that permanently trap it in the subsurface. And this is what we would do to enable us to store CO2 in these geological formations. So we have looked a little bit at how we can get samples of rock to examine and understand using a drill bit, those rocks underneath the seabed. We have looked at the samples of rock that we obtain and seen how they look like when they are suitable for storage, and how when they are fine-grained and impermeable and suitable to trap stored fluids within the subsurface. In our demonstration, we saw that in a porous rock, just how much fluid, in our case CO2, would be stored within rocks such as these, and how they become contained and permanently trapped in the subsurface by impermeable rocks such as these. Porous geological formations, like this one, underlie the seabed around Scotland and the UK. Each of these formations can be tens to hundreds of metres thick. Using the core samples and seismic survey data, we're able to map the extent of storage formations such as these around Scotland and the UK. There are many of these. They are at least 10 to hundreds of metres thick. They are more than half a mile beneath the seabed, and the formations can be tens to hundreds of kilometres in extent. The strata overlap each other. These storage formations are overlain by cap rocks and storage formations, so they are interleaved to be able to store very much more CO2 in the subsurface. If we're able to calculate the CO2 storage capacity for the total of these formations, we are able to store 4,600 million tonnes of CO2. That is 200 years' worth of CO2 emissions from Scotland.